Hey, welcome. Today we're going to break down a concept that is, no joke, the absolute bedrock of chemistry. It's the one thing that lets us connect the tiny, invisible world of atoms to the world we can actually see and measure. We are talking about the mole. So let's jump in and make this essential tool make perfect sense.
So think about it. It all kicks off with this massive problem. You can't see an atom. You definitely can't pick one up and put it on a scale. So how in the world do you count them when you're trying to run a chemical reaction? It's not like you can just grab a dozen atoms. Or maybe you can? This is the exact puzzle that the mole was created to solve.
And here is the brilliant solution chemists came up with. The easiest way to think about a mole is as a chemist's dozen, right? We all know a dozen is just a convenient word for 12 of something. Well, a mole is the exact same idea, but it's built for the unbelievably small world of atoms and molecules. It's just a way to group a truly enormous number of particles into one single easy-to-use unit.
Okay, so here's our game plan. We're going to build this thing from the ground up. We'll start with what a mole actually is. Then we'll see how it makes chemical equations come alive. From there, we'll learn how to use it like a recipe in this thing called stoichiometry, use it to crack the code of chemical formulas, and finally, we'll check out some seriously powerful shortcuts it gives you.
All right, let's dive right in. What exactly is a mole? I mean, we need a super precise scientific standard to build everything on, and that's exactly where we're going to start. Okay, this is the official textbook definition. And yeah, it sounds a little complicated, I get it. But the main idea is actually pretty simple. Scientists just needed a universal reference point, a standard that everyone could agree on. So they picked a specific type of carbon, carbon-12, and basically said, however many atoms are in exactly 12 grams of this stuff, we're going to call that number 1 mole. That's it. It's our benchmark.
And that magic number, it's this one, 6.022 times 10 to the 23rd power. It's called Avogadro's number, and you have to understand this number is mind-bogglingly huge. I mean, it's a 6 with 23 zeros after it. So 1 mole of anything, whether it's iron atoms, water molecules, or even basketballs, has this exact number of particles in it.
Now, here's where things get really cool, especially with gases. It turns out that at a specific, standardized set of conditions, which chemists call standard temperature and pressure, or STP for short, 1 mole of any gas you can think of will always take up a volume of 22.4 liters. This is called the molar volume, and trust me, it's a super useful shortcut when you're doing calculations with gases. So you see, the mole is basically our bridge. It connects the invisible world of single atoms to the measurable world of the lab. It's the concept that lets you look at the periodic table, see the atomic mass for carbon is about 12, and know that 1 mole of carbon atoms will weigh 12 grams. It works for whole molecules too. The mole's mass in grams is just its total molecular mass. It's how we weigh out atoms. And this just shows how incredibly versatile the mole is. It's like this central hub in chemistry that connects everything. It connects the mass we can weigh on a scale, to the exact number of particles, to the volume of gases, and even to the concentration of solutions. It is the concept that ties all of quantitative chemistry together. Okay, so now we know what a mole is, but why do we care so much? What's the big deal? Well, it turns out the mole is basically the star of the show in every single chemical reaction. It's what turns a simple list of chemical symbols into a precise, usable recipe. You know, a chemical equation really tells us 2 different stories at the same time. On one hand, you've got the qualitative story, the what is happening. It tells us which chemicals are involved, whether they're solid, liquid, or gas, and what kind of reaction it is. But on the other hand, thanks to the mole, we get the quantitative story, the how much is happening. Those big numbers in front of each chemical, they aren't just counting molecules, they're counting moles. They give us the exact recipe, which lets us measure and predict what's going to happen with amazing accuracy. And that brings us to the most practical application, stoichiometry. Yeah, it's a big, fancy word, but all it really means is using those mole ratios from an equation to calculate how much stuff you'll make or need. It's basically just chemical accounting. You're just following the recipe. The whole process, which people often call the mole method, is actually super logical. First, you've got to have a balanced equation. That's your non-negotiable recipe. Second, you take whatever amount you're given, which is usually in grams, and you convert it into moles. Third, and this is the key step, you use the mole ratio from your balanced equation to figure out how many moles of the other substance you're interested in. And finally, you just convert those moles back into grams so you have a useful, measurable number. Let's actually see it in action. Let's say we want to know how much carbon dioxide we can get from 12 grams of carbon monoxide. Okay, step 1. Convert that 12 grams of CO into moles. We just divide by its molar mass, which is 28, and we get 0.428 moles. Now, step 2, we look at our recipe. The balanced equation shows a 2-to-2 ratio between CO and CO2, which is just a 1-to-1 ratio. Simple. That means for every mole of CO we start with, we make 1 mole of CO2. So we're going to produce 0.428 moles of CO2. The last step, we turn that back into grams by multiplying by the molar mass of CO2, which is 44, and boom, we get our answer, 18.9 grams. See how that works? But the mole isn't just for reactions. It's also absolutely essential for figuring out what a compound even is in the first place. We can use it to find a compound's empirical formula, which is really just the simplest whole number ratio of atoms inside it. The logic here is just a really clean step-by-step process. Let's imagine we have a 1-gram chunk of some mystery iron sulfide compound. We analyze it and find out it's made of 0.465 grams of iron and 0.535 grams of sulfur. Okay, first step is always to convert those masses into moles. Now, that gives us a ratio, but the numbers look kind of messy. So for the next step, we do a little trick. We divide both of those mole amounts by whichever one is smaller. In this case, the 0.00833 moles of iron. That cleans everything up beautifully and gives us a simple ratio of 1 atom of iron for every 2 atoms of sulfur. And just like that, we've cracked the code and found our empirical formula, FeS2. Okay, now for the really, really cool part. Once you get the hang of the basics, the mole unlocks some incredibly powerful shortcuts for solving problems. And the most important one is called the principle of atom conservation. So take a look at a problem like this. At first glance, it looks like an absolute nightmare, right? We have some starting stuff, and it goes through a whole bunch of reactions that we don't even know to turn into this ridiculously complicated product. How could we possibly solve this without knowing every single intermediate step? Well, the secret is right here in this idea. We don't need to know the journey. All we need to know is one fundamental rule of the universe. Atoms are conserved. You can't create or destroy them in a chemical reaction. So, that means every single carbon atom that we started with in our potassium carbonate has to be in that final product somewhere. We just have to follow the carbon. And this is where the magic happens. Instead of getting lost in a bunch of unknown reactions, we just focus. We calculate the moles of carbon we started with. Then we look at that crazy final product and see that each molecule of it has 12 carbon atoms. Since the carbon had to come from somewhere, the moles of carbon we start with must equal the moles of carbon we end with. We can set up one simple equation, solve for the one thing we don't know, the weight of the product, and we get our answer, 11.6 grams. It turns a nightmare problem into simple algebra. It's a massive shortcut. Here's another classic type of problem you'll see. Analyzing a mixture. We've got 2 different metals, both reacting to make the same thing, hydrogen gas. We know the total weight of the metal mix and the total volume of gas they made. So how do we figure out how much aluminum we started with? And once again, the mole is the key that cracks the case. We know the total volume of hydrogen gas at STP, so we can easily calculate the total moles of hydrogen gas. We also know the specific mole ratios for how both zinc and aluminum make hydrogen, so we can build one single equation. The moles of hydrogen that came from the zinc plus the moles of hydrogen that came from the aluminum has to equal the total moles of hydrogen we collected. This gives us one equation with just one unknown variable, the weight of the aluminum, which we can then solve for directly. All right, let's just quickly recap the big ideas here. The mole is chemistry's universal counting unit, that giant number 6.022 times 10 to the 23rd. It is the essential connection between mass, gas volume, and the actual number of particles. Remember, chemical equations are just recipes written in moles, and stoichiometry is how we follow that recipe to predict what's going to happen. And finally, don't forget that atom conservation is your ultimate secret weapon for solving those really tough, complex problems. Look, the mole isn't just some random number you have to memorize for a test. It's a tool. It's a key that lets you understand and actually measure the world on a molecular level. It lets you ask and answer incredibly precise questions about everything around you. So I'll leave you with this question. Now that you know how to count atoms, what chemical mystery would you want to solve first?